Salam, peace be upon you. My name is Muhammad Laiq Siddiqui, the father of Holophase. Part 20 Universe as Cellular Automaton Local Rules, Global Worlds. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once: time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and the motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. You are journeying deeper into Book 9.5, Computational Generation, in Episode 9. Our previous step was a revelation. We began to see the holophase field not just as a description, but as a programming language, with derivative rules as instructions and time evolution as execution. This shifted our view of the universe from a static story to an active computation. But a question naturally arises. What is the architecture of this cosmic computer? Is it a monolithic, centralized processor, or is it something more distributed, more fundamental? Today, in Part 20, Universe as Cellular Automaton, we explore perhaps the most compelling and elegant architectural model, the universe as a massively parallel, discrete cellular automaton. We will see how the continuous, smooth phi field of our previous understanding can emerge as the large-scale limit of a vast grid of simple, identical cells, each following a tiny set of rules based only on its immediate neighbors. Our anchor image is a gigantic, hyperdimensional chessboard that fills all of space and time. But this is no ordinary chessboard. Each square, each cell, holds not a chess piece, but a number, a phase value. And instead of a single player making moves, every cell on the board, simultaneously and in unison, updates its own number based on a simple formula that looks at the numbers in the cells adjacent to it. From this unimaginably vast chorus of local, mindless updates, global patterns emerge: waves that sweep across the board, stable vortices that spin like tiny storms, intricate and persistent structures that move and interact. This is the dream of the cellular automaton model of the universe. And today, we will learn how the holophase field phi is the perfect bridge between this discrete computational dream and the continuous physical reality we experience. Here is the captivating puzzle of this part. We have developed a continuous, smooth description of reality in terms of the phi field and its differential equations. Yet, our most powerful tools for simulating this reality, our digital computers, work by discretizing space and time into a grid of pixels and time steps running local update rules. Are these simulations merely convenient approximations? Or could they be revealing a deeper truth, that the universe's fundamental machinery is itself discrete and local, with continuity and smoothness being large-scale illusions? Can we construct a discrete cellular automaton whose large-scale, average behavior is exactly described by our continuous phi equations? The answer is a profound and promising yes in principle. The journey from a cellular automaton, CA, to a continuous field theory involves two key conceptual steps: discretization and the continuum limit. First, discretization. Imagine we take continuous space and superimpose an infinitely fine grid, a lattice. At each lattice point, we store a number representing the value of the phi field at that location. Time is also chopped into discrete steps: tick, tock, tick, tock. Now we need an update rule. This rule takes the phi values at a cell and its immediate neighbors, perhaps also including the cell's old value from the previous time step, and computes the new phi value for that cell for the next time step. For a physics like CA, this rule is designed to mimic a physical law. A simple wave equation, for instance, can be approximated by a rule that says your new value will be the average of your neighbor's old values minus your own old value from 2 steps ago. This is a local rule. It only needs information from a tiny neighborhood. Second, the continuum limit. This is where magic happens. We now imagine making the grid spacing infinitely small and the time step infinitely short. We ask, as we do this, what equation does the collective behavior of our CA obey? Through careful design of the local update rule, we can make it obey, in the limit, exactly the continuous differential equations we derived from the action S phi. The spatial average of many cells becomes a smooth field. The finite difference between neighboring cells becomes the spatial derivative k. The change over one time step becomes the time derivative omega. The CA rule becomes the Euler-Lagrange equation in the limit of infinite resolution. So here is the breathtaking synthesis. The universe could be fundamentally a cellular automaton, a vast, discrete computer operating with perfect local rules. The smooth, continuous phi field we talk about is not the fundamental substance. It is the emergent, large-scale description of the collective state of this automaton, just as the smooth flow of a fluid emerges from the chaotic motion of trillions of discrete molecules. In this view, empty space is not passive nothingness. It is the grid itself, actively processing information at every node. Let's explore the triunity of the cellular automaton perspective, the time echo of the automaton, the clock cycle of reality. Time becomes a sequence of discrete update cycles. The cosmic processor has a fundamental clock speed, the Planck time, perhaps. At each tick, every cell in the universe updates its state based on the previous state of its neighborhood. The time echo is this universal synchronized clock step. It gives time a granular computational rhythm at the most fundamental level, even though at our scale it appears smooth and flowing. The space echo of the automaton, the fabric of the grid. Space is not a smooth continuum, but a network of cells, each with a finite number of neighbors, its von Neumann neighborhood, or Moore neighborhood. The geometry and dimensionality of this grid define fundamental space. The space echo is this lattice structure. It suggests that at scales near the Planck length, space itself might have a discrete geometric property that could manifest in exotic ways, like violations of continuous Lorentz symmetry at ultra-high energies. The motion echo of the automaton, emergent kinematics. What we perceive as motion, a planet's orbit, a light ray's path, is the large-scale pattern of state changes propagating through the grid. A wave is not a thing moving. It is a correlated pattern of cell updates that shifts its locus across the lattice over many time steps. A particle like soliton is a stable, self-reinforcing pattern of cell states that maintains its identity as it propagates. The motion echo is pattern propagation in a discrete medium. Now, let's locate this profound model on the master tree. We are on the Cellular Automaton branch within book 9.5, Computational Generation. This branch depends directly on the parent node of Phi as a programming language, as it provides a specific, concrete architecture for that programming language's execution. It enables the next exciting explorations, algorithmic information, measuring the complexity of Phi patterns, and novelty generation, understanding how simple rules can produce endless new, unpredictable patterns. It also provides a natural bridge to quantum foundations, with models like quantum cellular automata offering a discrete picture of quantum field theory. To make this abstract grid universe tangible, let's illuminate our path with lanterns from simulations, nature, and technology. A near lantern from classic computer science, Conway's Game of Life. This is the most famous cellular automaton. It's a 2D grid of square cells, each either alive or dead. The rules are simple. A live cell with 2 or 3 live neighbors stays alive. Otherwise, it dies. A dead cell with exactly 3 live neighbors becomes alive. From these utterly local, simple rules, astounding complexity emerges. Gliders, patterns that move diagonally, oscillators, guns that emit gliders, even self-replicating patterns. The Game of Life is a toy universe that demonstrates how global complexity and apparent motion can arise from static, local rules. It is a proof of concept for the entire idea. Our phi-based CA would be vastly more complex, continuous valued cells, rules mimicking calculus, but the philosophical principle is identical. A middle lantern from materials science, crystal growth and dendritic patterns. When a metal solidifies from a melt, atoms attach to the growing crystal in a lattice. The process can be modeled beautifully by a probabilistic cellular automaton. Each grid site represents a possible atom location. Rules govern whether a liquid site becomes solid based on the number and arrangement of solid neighbors, modeling bonding, and temperature, a probability. Running this CA produces intricate, branching, snowflake-like dendritic structures that match real metallurgical micrographs. Here, a CA doesn't just mimic physics, it provides the actual mechanistic model for a real discrete process, atomic attachment, that leads to continuous-looking patterns at larger scales. A far lantern from theoretical physics. Causal Dynamical Triangulations, CDT. This is a serious research program in quantum gravity. It models spacetime itself as a cellular automaton of sorts. Instead of a fixed grid, it uses tiny building block shapes, simplices, like 4D triangles, that are glued together dynamically. The update rule is a sum over all possible ways to connect these blocks that respect causality. In the large-scale limit, this discrete combinatorial model spontaneously generates a smooth, four-dimensional spacetime geometry that obeys the classical equations of general relativity. This is a direct and cutting-edge example of the universe as automaton idea being used to derive the very fabric of spacetime from discrete, algorithmic principles. From the game of life to crystal growth to the emergence of spacetime itself, a powerful theme resonates. Complex, continuous, dynamic behavior can be the effective, large-scale description of a system built from simple, discrete, local parts following immutable rules. The universe may be the ultimate example. What then is the specific language role of the cellular automaton model within Holophase? It is the implementation architecture. It proposes a specific mechanistic answer to the question, on what hardware is the phi program running? The answer? On a spatial grid of simple processors, cells, connected to their immediate neighbors. The continuous phi language is the high-level programming language. The CA is the machine code executed on the distributed hardware of reality. The core question this part asks about phi is, can the continuous differential equations governing phi be recovered as the continuum limit of a discrete cellular automaton with local update rules? And if so, what are the properties of that underlying automaton? We are moving from the software level, the equations, down to the proposed hardware level, the discrete grid. What does this CA perspective do for our understanding? It provides a conceptually simple, mechanistic picture of how physics could be implemented at the most fundamental level. It demystifies locality. Influences spread no faster than one cell per time step, offering a natural mechanism for the speed of light limit. It suggests a natural origin for quantization. If the grid has a fundamental scale, then some quantities, like action, might be naturally quantized in units of that scale. It connects physics to computer science and the theory of computation in the deepest possible way. Now, stability and breakdown. The CA model is a hypothesis about fundamental architecture. As a mathematical construct, it is perfectly consistent. Its ability to approximate continuum physics in the limit of fine grid spacing is a theorem for many well-designed rules. It breaks down as a complete description if experiments ever find irreducible evidence against locality or discreteness at some scale. For example, if violations of Lorentz symmetry, which a fixed grid might imply, are conclusively ruled out at all energies, or if quantum entanglement is shown to involve truly instantaneous correlation without any underlying local mechanism, a contentious point, then a simple classical CA model would be in trouble. However, more sophisticated models, quantum cellular automata, can address some of these challenges. This brings us to our empirical grounding, falsifiability. The claim that a system can be modeled as a phi-based cellular automaton is a stringent one, with clear empirical implications, especially for the behavior of simulations and the detection of underlying discreteness. The central claim: any physical system accurately described by Holophase field phi can be simulated to arbitrary accuracy by a cellular automaton with an appropriate local update rule, provided the grid spacing and time step are sufficiently small compared to the relevant physical scales. Furthermore, as the grid is refined, the CA's predictions must converge smoothly to the continuum phi equations predictions. Any observed physical phenomenon should, in principle, be reproducible by such a CA simulation. A concrete measurement scene, simulating wave propagation in a nonlinear medium. We choose a well-understood nonlinear system, shallow water waves in a long, narrow channel, a water tank. We have precise continuum equations for this, the Korteweg-de Vries equation, which has soliton solutions. We then create a 1D cellular automaton model. Each cell represents a segment of the water channel, storing a number for the water's height, phi. The update rule is designed to approximate the KdV equation using finite differences for derivatives and a discrete nonlinear term. We run the CA simulation on a supercomputer, starting with an initial condition matching a real experiment, a single hump-shaped wave. We run the simulation at various grid resolutions, coarse, medium, fine. In the real tank, we generate the same initial hump and use wave probes to measure the water height over time and space as the wave evolves. The pass condition, validation. At coarse resolution, the CA simulation shows artifacts. The wave moves at a slightly wrong speed or shows stair-step patterns. As we increase the resolution, finer grid, smaller time step, the CA's output converges. At very high resolution, the simulated wave profile over time becomes visually indistinguishable from the high-precision experimental measurements. It reproduces the soliton's stable shape, its speed, and how it interacts with other waves. The convergence is smooth and systematic, following the predicted scaling laws of the numerical method. This demonstrates that the continuum physics is the limit of the discrete CA dynamics. The fail condition, falsification. The CA simulation, even at extremely high resolution, fails to match the experimental data. It consistently produces artifacts, like unnatural oscillations, persistent dispersion, or incorrect stability properties, that do not diminish with finer grids. Even more telling, if we discover that no possible local update rule on a grid can reproduce a key observed phenomenon, for instance, the exact statistical distribution of outcomes in a quantum experiment, like the double slit pattern, then the system cannot be modeled as a classical local CA. This would be evidence for a fundamentally different kind of underlying process, perhaps inherently non-local or continuous in an essential way. Such a finding would challenge the CA hypothesis for that domain of physics. This falsifiability ensures that the elegant idea of a universe as CA remains engaged with the hard task of actually matching empirical data. Let's cultivate a practical recognition skill. You can train your eye to see cellular automaton-like logic in any system where global behavior arises from many identical, simple parts, interacting only with their immediate surroundings, and where the rules are the same everywhere. Watch the flashing patterns of a field of fireflies that synchronize. Each firefly's flash depends on seeing the flashes of its nearby neighbors. A simple local rule, if you see a flash, flash soon after, can lead to vast waves of synchronized flashing sweeping across the field. This is a biological, probabilistic CA in action. Observe the formation of traffic flow patterns on a highway. Model each car as a cell on a 1D grid. The rule: if the cell in front of you is empty, move forward. If it's occupied, stop. This extremely simple Rule 184 CA produces traffic jams, free-flowing regions, and shock waves that move backward, all emergent phenomena from local driver behavior. Consider the spread of a rumor in a close-knit village. Each person, a cell, has a state, knows the rumor or doesn't. The rule: if you hear the rumor from a neighbor, you start telling it to your other neighbors. The pattern of rumor spread is a diffusion-like process emerging from purely local communication. Whenever you see complex global order arising from simple, repetitive local interactions, you are witnessing the conceptual core of a cellular automaton. You are seeing local rules building global worlds. We must connect this architectural vision deeply to our Holophase journey. In the previous part, we saw Phi as a programming language. Here, we have proposed a specific, plausible hardware architecture for running that language, the spatial grid automaton. This completes a powerful loop. The continuous descriptive language of physics, Phi, can be seen as the emergent large-scale theory of a discrete computational substrate. The generative grammar is the algorithm. The CA is the physical computer it runs on. We haven't added new metaphysical baggage. We've proposed a concrete mechanism for how the grammar gets physically executed. If you want to see the full mathematical derivations and exact equations behind this idea, the formal construction of lattice field theories, the derivation of continuum limits, the analysis of stability and convergence for finite difference schemes, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. Let us pause and appreciate the grandeur of this vista in Book 9.5. We have now journeyed from seeing the universe as a story, to seeing it as a computation, to now seeing it as a specific kind of computer, a colossal, spatially extended cellular automaton. This view is both humbling and empowering. It suggests that the deepest laws may be simple rules of neighborhood interaction, and that all the richness of existence is an emergent pattern unfolding on a grid of unimaginable fineness. In the next part, we will ask a profound question enabled by this computational view. Where does novelty come from? If the universe is a deterministic automaton following fixed rules, how can it generate truly new, unpredictable, complex structures? Life, consciousness, ideas? We will explore algorithmic information and novelty generation, seeing how even simple programs can produce outputs that are incompressible and essentially new, providing a computational understanding of creativity and the open-endedness of cosmic evolution. Before we end, the mandatory zoom out to hold our scope. The Cellular Automaton model, for all its mechanistic appeal, is still just a proposed implementation of the Holophase grammar. The grammar itself, phi, its derivatives, the action, remains the invariant core. Whether the underlying hardware is a continuous field or a discrete grid, the observable, large-scale laws are described by the same continuum equations. One field, phi, plus its infinite tower of derivative questions, can be seen as either the fundamental substance or the emergent language of a deeper computation. Both views are contained within the holistic framework of the generative grammar. As we conclude, hold the image of the infinite cosmic chessboard. Each cell is a humble processor, knowing only its neighbors. Each tick of the clock, they all recalculate. From this unfathomably vast, simple, synchronous process, the galaxy's whirl, the planet's orbit, the waves crash, and the mind contemplates itself. The universe is not just like a cellular automaton. If this view is correct, it is one. And we, in this moment, are a fleeting, beautiful, and self-aware pattern being computed in its boundless, ongoing game. Salam, and peace be upon you.